As October 29th approaches, a question burns across the night sky. Why did NASA lie that 3I Atlas would vanish? They told us it would slip behind the sun, hidden, unobservable, and lost in the glare of our own star. But the sky remembers what they wanted us to forget. Independent astronomers never stopped watching, and what they captured changes everything. 3I Atlas isn't gone. It's right there, beside the sun, brighter, faster, and breaking every prediction written about it. So if NASA knew this, why the silence? Why did they lie? Stay with me until the end, because tonight we reveal what NASA didn't want us to see. All along, the truth was never in the dark, it was right there, in the light. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1, Dramatic Framing. October 29th, 2025. The date was supposed to mark the disappearance. NASA told us to look away. They said the interstellar visitor designated 3I Atlas would slip behind the sun, vanishing into solar glare, unobservable by any telescope on Earth. The message was clear. The show's over, folks. Come back in December when it emerges on the other side. But here's the problem with telling people not to look. Some of them look anyway. Independent astronomers, the kind who stack images in their basements and share data on obscure forums, kept their instruments trained on that patch of sky. They didn't wait for permission. They didn't accept the blackout narrative. And what they captured wasn't an absence. It was a presence. 3I Atlas wasn't hiding behind anything. It was glowing, moving, behaving in ways that shattered every prediction the official sources had published. The images started trickling out on October 28th, 29th, 30th. Not from NASA, not from the European Space Agency, from regular people with telescopes and an internet connection. So let me ask you something. When a space agency with billion-dollar budgets and instruments scattered across the solar system tells you an object is unobservable, and then a hobbyist in New Mexico captures it anyway, what does that mean? Was it an oversight, a miscalculation of viewing geometry, or was it something else entirely? Because the data these independents are sharing doesn't just contradict NASA's timeline, it contradicts the physics we expected this object to follow. This isn't just a story about a comet, it's a story about credibility. It's about who controls the narrative when something inexplicable appears in our sky. It's about what happens when the institutions we trust to watch the cosmos tell us to avert our eyes at the exact moment something unprecedented occurs. And it's about the implications, the ones nobody wants to say out loud, the ones that suggest 3I Atlas might not be a comet at all. You're about to see the official version, the one NASA published. You're about to see the counter-evidence, the images that shouldn't exist, the brightness curves that don't make sense. You're going to hear about jets of material pointing the wrong direction, about speeds that deviate from gravitational prediction, about a composition so strange that peer-reviewed papers are using words like extreme and anomalous. And then you're going to have to decide what you believe. Because when this thing emerges from its supposed hiding place in December, assuming it follows any predictable path at all, we're going to find out if the independent observers were right. We're going to find out if NASA was protecting us from information, or protecting information from us. And we're going to confront a possibility that science fiction has entertained for decades, but that institutional astronomy has studiously avoided. What if something out there isn't natural? What if it's watching us the same way we're watching it? The question isn't whether 3I Atlas is strange. The question is how strange, and who knew, and when they knew it. The geometry of the solar system doesn't lie. The brightness of an object captured by multiple independent sources doesn't fabricate itself. The timing of public statements versus the timing of actual observational windows doesn't align by accident. So what are we not being told? Later in this investigation, you're going to see orbital diagrams that explain why behind the sun is sometimes a convenient phrase that obscures more than it clarifies. You're going to see stacked images from Mars-based cameras, frames from solar coronagraphs, amateur captures that show an object exactly where NASA said it wouldn't be visible. You're going to hear speculation about non-natural acceleration, about techno-signatures, about the possibility that 3I Atlas is using its close approach to the Sun for something other than passive heating. And here's the thing that keeps me up at night. If the independent observers are correct, if this object was visible during the period we were told it wasn't, then every press release, every public briefing, every casual mention of an observational blackout becomes a choice, not a mistake. A choice. And choices have reasons. So what was the reason? We live in an era where citizen scientists can outpace billion-dollar institutions, where machine learning algorithms can flag anomalies faster than human review boards, where a Reddit thread or a Medium post can marshal evidence that challenges decades of accepted practice. The democratization of astronomy means we don't have to wait for permission to see what's in our sky. But it also means we inherit the responsibility of interpretation. And interpretation without context is just speculation wearing a lab coat. So buckle up. This is going to be a journey through contradictory data, through institutional silence, through the uncomfortable space between what we were told and what actually happened. You're going to come out the other side with more questions than answers. But at least you'll know what questions to ask. At least you'll know where to look when 3I Atlas reappears, if it reappears, and if it reappears the way we expect. Because October 29th wasn't an ending, it was barely even a beginning. Part 2. Official Narrative. NASA, an astronomical community position. Let's start with the official story, the baseline everyone was supposed to accept. NASA discovered 3I Atlas on July 1st, 2025, using the Asteroid Terrestrial Impact Last Alert System survey based in Chile. The designation 3I marks it as the third confirmed interstellar object ever detected, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Right from the start, astronomers knew this was special. The trajectory was hyperbolic, meaning it wasn't bound to our Sun. It came from somewhere else and it was just passing through. The orbital calculation showed a perihelion, the closest approach to the Sun, occurring around October 29th or 30th, 2025. At that point, the object would reach a distance of approximately 1.36 to 1.4 astronomical units from the Sun. That's actually farther than Earth's orbit, farther than Mercury or Venus ever get. So why the blackout narrative? Because of viewing geometry. From Earth's perspective, as 3I Atlas approached perihelion, it was moving into a position where the Sun would be directly between us and the object, or close enough that solar glare would overwhelm any telescope trying to observe it. NASA published visibility schedules. They said ground-based telescopes could track 3I Atlas through September. After that, solar conjunction would render it unobservable until December, when it would emerge on the far side of the Sun and become visible again in pre-dawn skies. This framing makes sense if you understand elongation angles. When an object gets within a certain angular distance from the Sun as viewed from Earth, maybe 15 or 20 degrees, the sky's too bright for conventional telescopes to function. You're essentially trying to spot a flashlight next to a spotlight. The brightness differential is impossible to overcome without specialized equipment. And NASA did clarify, in technical documents at least, that specialized instruments might still catch glimpses. Solar coronagraphs, instruments designed to block out the Sun's disk and observe the corona, can sometimes detect comets passing very close to the Sun. But for the general astronomy community, for amateur observers with backyard telescopes, the message was consistent. October through early December equals blackout period. Don't waste your time looking because you won't see anything. The Hubble Space Telescope had already gathered data earlier in the year, constraining the size of the nucleus. The estimates suggested a relatively small object, a few kilometers across at most, with significant cometary activity. The speed was clocked at approximately 60 kilometers per second inbound, typical for interstellar visitors that aren't gravitationally bound to the solar system. NASA classified 3I Atlas as an active comet rather than an inert asteroid, based on the presence of a visible coma, the cloud of gas and dust surrounding the nucleus. Then came the James Webb Space Telescope observations in August 2025. The near-infrared spectrograph detected a coma dominated by carbon dioxide. Not water vapor, which is the primary volatile in most comets from our solar system, but carbon dioxide. That was the first hint of strangeness, but NASA framed it as consistent with an object formed in a cold, distant protoplanetary disk, where carbon dioxide ice could dominate over water ice. Unusual, yes. Impossible, no. The peer-reviewed papers started appearing on archive.org, the preprint server, describing the composition as exotic but explicable. NASA's public communications used phrases like passing too close to the sun to observe, and behind the sun interchangeably, which to a trained astronomer means the same thing in practical terms. You can't observe it because of solar interference, but to the general public, those phrases carry different connotations. Behind the sun sounds like the object is physically occluded, blocked from view by the sun's body. Too close to observe sounds more technical, more about instrumentation limits. And that semantic difference matters when you're trying to evaluate whether NASA was being precise or whether they were shaping perception. From NASA's institutional perspective, there was no deception. They were following standard practice. When an object enters solar conjunction, you publish the blackout dates, you alert observers that the window is closing, you schedule follow-up observations for when it re-emerges. You don't keep updating the public every day during the blackout because there's nothing to report. The object is doing what physics says it should do. It's following a predictable orbit. It's losing visibility according to geometry. End of story. Except the story didn't end there. Because while NASA was publishing blackout warnings, independent observers were stacking frames from solar observatories, from Mars orbiters, from coronagraph instruments that the general public barely knows exist. And those observers were seeing something, not nothing. Something. Something bright enough to register. Something moving in ways that didn't perfectly match the published ephemeris, the predicted position table. Something that raised a question NASA hadn't anticipated anyone would ask. If 3i Atlas was supposed to be unobservable, why was it being observed? Part 3. Counter-narrative emerges. Independent, shucked, amateur observers speak. Here's where the cracks appear. October 28, 2025. A post appears on a citizen science forum. The user has stacked coronagraph images from the GOE's satellite, a solar monitoring platform operated by the National Oceanic and Atmospheric Administration. GEOS wasn't designed to hunt comets. It watches the sun for space weather events, coronal mass ejections, solar flares. But its coronagraph instrument blocks out the sun's disk and captures the surrounding corona, and in that field of view, faint objects sometimes appear. The user claimed to have detected a brightness spike consistent with cometary activity right where 3i Atlas should have been, assuming the published orbital elements were accurate. But NASA had said it would be unobservable, so either the user was wrong, misidentifying noise or an artifact, or NASA's blackout. Framing was incomplete. The post included timestamps, image registration details, stacking methodology. It wasn't a blurry photo with a circle drawn around a random pixel. It was methodical, and it got attention. Then came the Mars angle. On October 3rd, 3i Atlas passed relatively close to Mars, close enough that some astronomers speculated Mars-based cameras might catch it. The Perseverance rover carries navigation cameras and the Mastcam-Z instrument, a high-resolution stereo imaging system. Those cameras point at the Martian surface most of the time, but they can be commanded to look at the sky. And according to at least one independent post, someone claimed to have found evidence of 3i Atlas in publicly released Perseverance image archives during that flyby window. Now, Mars-based observations are tricky. The cameras aren't optimized for faint astronomical targets, the exposure times are short, the field of view is limited. But Mars had a different vantage point than Earth during early October. From Mars, 3i Atlas wouldn't have been in solar conjunction yet. The geometry was different. So if Perseverance did capture frames showing the object, that wouldn't contradict NASA's Earth-based blackout claim. It would just add data from a perspective NASA hadn't emphasized in their public messaging. Amateur astronomer forums started lighting up. People were comparing notes, sharing image stacks, cross-referencing timestamps with orbital predictions. Some claimed to see a faint tail structure in coronagraph data. Others pointed out brightness fluctuations that seemed inconsistent with a simple rotating nucleus model. A few flagged what they called anomalous orientation, jets of material that appeared to be directed sunward rather than away from the sun, which violates the basic expectation that solar radiation pressure pushes cometary dust and gas outward. One Medium-style article argued explicitly that 3i Atlas was not behind the sun in any meaningful sense. The author walked through the geometry, calculated the elongation angles from multiple observation platforms, and concluded that while Earth-based conventional telescopes were indeed blocked, other instruments, particularly solar coronagraphs and Mars-based cameras, should have maintained visibility, And if they maintained visibility, then the blackout narrative was, at minimum, an oversimplification. The credibility question looms large here. Independent observers don't have the same calibration standards, the same peer review, the same institutional backing as NASA. Their images might include artifacts from stacking, hot pixels, cosmic ray strikes, registration errors. Their processing might introduce biases, their conclusions might overreach. But the pattern was persistent. Multiple sources, multiple instruments, multiple users all flagging something where NASA said there should be nothing observable. And then there were the brightness reports, several. Independents claimed 3i Atlas appeared brighter than predicted during the conjunction window. Cometary brightness follows a power law based on distance from the Sun and distance from Earth. You can predict how bright a comet should be at any given time if you know its size, its activity level, and its trajectory. But if the independent observations were accurate, 3i Atlas was outperforming expectations. It was glowing more intensely than the simple model suggested, which could mean the nucleus was more active than estimated, or the dust production was higher, or something else was going on. The emotional framing here is important. This is the democratization of observation in action. These are people who didn't wait for NASA's permission to analyze data. They pulled publicly available coronagraph frames. They scraped Mars rover archives. They shared files on Discord servers and Reddit threads. They weren't trying to undermine NASA. They were trying to see what was actually happening. And what they were seeing didn't match what they'd been told to expect. So now you have two narratives running in parallel. NASA says the object is in blackout, essentially unobservable. Wait until December for the next viewing window. Independents say the object is visible right now through alternate instruments, and the behavior is anomalous. Who's right? And if both are partially right, what does that mean for trust, for transparency, for the way we handle unprecedented observations? Because if independent observers can catch what official channels miss, or what official channels choose not to emphasize, then the gatekeeping function of institutions starts to erode, and maybe that's healthy, or maybe it's chaos, but it's definitely happening. Part 4. Unexpected behavior, brightness, jets, speed deviations. Now let's talk about what makes 3i Atlas genuinely strange, beyond just the visibility debate. Because even if we accept NASA's baseline data, even if we set aside the independent observer controversy, this object exhibits behaviors that push the boundaries of normal cometary activity. And when you combine those behaviors with the disputed observations, you start to see why some people are asking uncomfortable questions. First, the carbon dioxide dominance. The James Webb Space Telescope detected a coma composition heavily weighted toward carbon dioxide rather than water vapor. Most comets in our solar system are water-rich because they formed in regions where water ice was the primary volatile. Carbon dioxide becomes dominant only in very cold formation environments or in objects that have lost their water through prolonged solar exposure. But 3i Atlas is an interstellar visitor, presumably on its first pass through the inner solar system, so it shouldn't have been depleted by previous perihelion passages. The carbon dioxide dominance suggests it formed in an environment colder or chemically different from the region where our solar system's comets originated. Then there's the polarization behavior. A paper published on archive.org described what the authors called extreme negative polarization in the reflected light from 3i Atlas. Polarization measures the orientation of light waves, and when light scatters off dust particles, the degree and direction of polarization depend on particle size, shape, and composition. Extreme negative polarization suggests either very unusual dust properties, very small particles, or a particle size distribution that doesn't match typical cometary dust. The paper didn't claim this was artificial, it just flagged it as anomalous, something requiring further study. Now add the independent claims about jet orientation. Comets develop jets when subsurface ices vaporize and burst through the crust, carrying dust with them. Solar heating drives this process, so you expect jets to form on the sunward side and point generally away from the sun, as radiation pressure pushes the material outward. But several independent posts claim to observe jets oriented sunward, toward the sun rather than away. If true, that would require either a rotational effect where the jet originates on the night side and sweeps forward, or some kind of active expulsion mechanism that overcomes radiation pressure. Brightness spikes add another layer. Comets can flare suddenly if a fresh ice pocket is exposed or if a chunk of the nucleus breaks off, increasing the active surface area. But the brightness reports from independents suggested intensification beyond what simple outgassing models would predict. And some of those reports came with timestamps during the conjunction window, when NASA said the object was unobservable. So either the brightness spikes happened earlier and the observers misdated them, or the brightness spikes happened during conjunction and the observers were actually seeing the object when they shouldn't have been able to. Then there's the trajectory question. 3I Atlas is on a hyperbolic orbit, which means it's not bound to the Sun. Gravity alone determines its path unless non-gravitational forces intervene. For comets, those forces usually come from outgassing. When material jets off one side of the nucleus, it creates a tiny rocket effect nudging the orbit. This is called non-gravitational acceleration, and it's well documented for active comets. But the magnitude and direction of that acceleration depend on the jet orientation and the mass loss rate. If 3I Atlas is producing jets with unusual orientations, or if the brightness implies higher than expected mass loss, then the trajectory might deviate slightly from pure gravitational prediction. No one has definitively measured such a deviation yet. The orbital element refinements are ongoing, but if future observations, especially after the December re-emergence, show that 3I Atlas didn't follow the predicted path precisely, that would be significant. It would mean either the outgassing model was wrong, or something else was influencing its motion, and that's where speculation starts creeping in. What if this isn't just outgassing? What if the jets are controlled, directed, pulsed in a way that produces thrust? What if the object is using its close approach to the Sun not just as a passive heating event, but as an opportunity to perform a maneuver, an Oberth-style trajectory adjustment where you fire a rocket, or in this case expel material, at the moment of highest velocity and closest solar proximity to maximize energy gain? That's a deeply speculative scenario. It requires attributing intentionality to an object we have no evidence is anything other than a natural comet. But it's the kind of scenario that starts to feel less absurd when you stack up the anomalies. Avi Loeb, the Harvard astronomer who argued that Oumuamua might have been artificial, has commented on the general possibility that interstellar visitors could be probes or artifacts from other civilizations. He developed something called the Loeb scale, a framework for assessing the likelihood that an object exhibits technosignatures. 3I Atlas hasn't been formally scored on that scale, but if you were to evaluate it, you'd be looking at things like deviation from natural motion, unusual composition, controlled orientation, non-random brightness fluctuations. And while none of those individually scream artificial, the combination starts to raise eyebrows. Here's the uncomfortable truth. We don't have enough data to rule anything out yet. The professional observations are consistent with an exotic but natural comet. The independent observations, if accurate, add anomalies that could still be natural but harder to explain. The speculative scenarios about artificial behavior remain exactly that, speculative. But the window for dismissing those scenarios entirely is starting to close. Because if 3I Atlas continues to surprise us when it re-emerges, if it deviates further from prediction, if it exhibits behaviors that outgassing alone can't explain, then the conversation shifts, and institutions that spent months assuring us it's just a comet will have some explaining to do. Part 5. Breaking the official silence. Timing and communication patterns. Let's map the timeline of what was said versus when it was said, because timing matters. July 1st, 2025, the Discovery announcement. NASA publishes a brief noting the detection of an interstellar visitor, hyperbolic trajectory, estimated perihelion in late October. The tone is measured, scientific, unalarmed. This is interesting, they say, but not unprecedented. We've seen interstellar objects before. August comes. Webb observations capture the carbon dioxide-dominated spectrum. NASA releases that data to the scientific community. Papers start appearing on archive.org. The language is cautious, unusual composition rather than anomalous, requires further study rather than defies explanation. This is standard scientific hedging, but it also means the public messaging stays calm even as the professional community starts flagging oddities. September. Ground-based observations continue. Amateur astronomers track 3I Atlas as it brightens. Some start noticing the polarization weirdness. NASA updates the visibility schedule, reminding observers that conjunction is approaching and that the object will soon be unobservable. The phrasing, too close to the Sun for ground-based telescopes, technically accurate, but also incomplete, Because it doesn't mention alternate observation platforms. October 3rd, Mars flyby. 3i Atlas passes relatively close to Mars. There's no immediate press release from NASA about Perseverance imaging attempts. Silence. Either the rover didn't look, or the images haven't been processed, or the data wasn't deemed significant enough to publicize. But that silence creates a vacuum, and vacuums get filled with speculation. October 15th through 25th, the ramp up to perihelion. NASA goes quiet. No new press briefings, no updated blog posts on the NASA Science website. The last substantive update was weeks earlier. Meanwhile, independent observers are starting to post their stacked coronagraph frames, their anomaly claims, their questions about why they're seeing something when they were told they wouldn't. And NASA says nothing. October 29th, perihelion, the day 3i Atlas makes its closest approach to the Sun. The day it was supposed to vanish. And the day independent observers claim it was at its brightest, its most active, its most visible through alternate instruments. Still no comment from NASA, no clarification, no acknowledgement of the independent reports, just silence. Now, November. Post-perihelion. The object is supposedly moving away from the Sun, still in conjunction, still unobservable by Earth-based conventional telescopes. And NASA's public communication channels remain largely dormant. There's a brief update on the NASA Science page reiterating the December re-emergence window, but no engagement with the independent observer claims. No explanation of why coronagraph data might show activity. No discussion of Mars-based observations. Nothing. Compare this with how Oumuamua was handled back in 2017 and 2018. That object also generated controversy and speculation about artificial origins. But NASA and the European Space Agency actively engaged with those claims. They published detailed rebuttals explaining why natural explanations were sufficient. They released data promptly. They participated in public discussions. The transparency wasn't perfect, but it was present. With 3i Atlas, the transparency feels thinner. The updates are sparse. The engagement with alternative claims is absent, and that silence, intentional or not, fuels suspicion. Because when an institution doesn't address anomalies publicly, people assume the anomalies are being suppressed. Maybe they're not. Maybe NASA is just waiting for peer-reviewed confirmation before commenting. Maybe they're prioritizing data quality over speed. But perception matters, and the perception right now is that NASA said don't look, and then stopped talking. There are rumors, unconfirmed, that high-resolution Mars orbiter data, specifically from the Mars Reconnaissance Orbiter's HiRISE camera, was requested by independent researchers and hasn't been released. HiRISE can theoretically image objects beyond Mars if commanded correctly. If such data exists and shows 3i Atlas during the conjunction period, that would be significant. But if such data exists and hasn't been made public, that raises questions about data release policies. NASA operates under a principle of open data. Observations from publicly funded missions are supposed to be archived and accessible, but there's always a proprietary period, a window where the primary investigator team has exclusive access before public release, and there are exceptions for data that might have national security implications, though it's hard to imagine how a comet would qualify unless someone thinks it's not a comet. The wording NASA chose matters too. Behind the Sun is a phrase that carries more narrative weight than unobservable due to solar glare. It suggests occlusion, invisibility, a blackout that's absolute. But astronomers know the reality is more nuanced. Coronagraphs exist. Mars has a different vantage. Space-based observatories might catch glimpses. By using the simpler, more dramatic phrase, NASA made their messaging more accessible, but also more vulnerable to the charge of oversimplification or misdirection. Is there a pattern here? Oumuamua, the first interstellar visitor, generated speculation about artificial origins. NASA eventually engaged, but only after public pressure mounted. 2I/Borisov, the second, was clearly a comet and generated minimal controversy. NASA was straightforward. Now 3i Atlas, the third, exhibits anomalies that fall somewhere between Oumuamua's mysteries and Borisov's mundanity. And NASA's response has been restrained to the point of opacity. The question is whether that restraint is caution or control, Are they being careful not to overstate conclusions based on incomplete data? Or are they framing the narrative to limit scrutiny until they've decided what the story is? Because in an age where citizen scientists can pull coronagraph frames and post them online within hours, institutional control of narrative is harder to maintain. And maybe that's what we're seeing here. Not a conspiracy, not a cover-up, just an institution struggling to adapt to a world where the public doesn't wait for permission to analyse and interpret. December will be the test, when 3i Atlas re-emerges, when professional telescopes get clean observations again. We'll see if the anomalies persist. We'll see if NASA's predictions held. And we'll see if the independent observers were vindicated, or if they were chasing artifacts and noise. Until then, the silence speaks louder than any press release ever could. Part 6. Viewing Geometry and Instrument Sensitivity. Let's get technical for a moment, because understanding the geometry is crucial to evaluating who's right. When NASA says an object is behind the Sun, they're using shorthand for a specific observational constraint called solar elongation. Elongation is the angular separation between an object and the Sun as viewed from a given location, usually Earth. When that angle gets small, say less than 20 or 30 degrees, the Sun's glare overwhelms any attempt to observe the object with conventional optical telescopes. Think of it like trying to spot a firefly hovering next to a stadium floodlight. The firefly is there, it's emitting light. But the floodlight is so bright that your eyes can't resolve the firefly against the glare. That's what happens during solar conjunction. The object doesn't disappear. It just becomes impossible to see with standard instruments because the sky's too bright. But not all instruments are standard. Coronagraphs are designed specifically to block out the Sun's disk and observe the surrounding corona. They use an occulting disk, a physical barrier that blocks the direct sunlight, allowing the much fainter coronal light and any foreground or background objects to be detected. Satellites like SOHO, the Solar and Heliospheric Observatory, carry coronagraph instruments that can detect comets passing very close to the Sun, sometimes just a few solar radii away. 3i Atlas at perihelion was much farther out, over 1 astronomical unit, but still within the field of view that coronagraphs can cover. So when independent observers claimed to detect 3i Atlas using coronagraph data, they weren't violating physics. They were using a tool specifically designed to overcome solar glare. NASA didn't lie when they said ground-based telescopes couldn't observe it. They just didn't emphasize that other instruments could. Now add Mars to the picture. Mars orbits the Sun at a different distance and at a different position than Earth. In early October 2025, Mars was not in the same line of sight configuration as Earth. From Mars, 3i Atlas would have had a different elongation angle, possibly larger, meaning less solar interference. The Perseverance rover and various Mars orbiters carry cameras capable of imaging the sky. They're not optimized for faint astronomical targets, but under the right conditions they can capture comets, asteroids, even distant galaxies. The Mars flyby on October 3rd gave those cameras a potential opportunity. If anyone commanded Perseverance to look at the right patch of sky with the right exposure settings, they could have captured 3i Atlas before it entered conjunction from Earth's perspective. And if those images exist, they would show the object during a period when NASA was already messaging the blackout narrative. Not because NASA lied, but because they were talking specifically about Earth-based visibility. Instrument sensitivity is another factor. Brightness limits, the faintest magnitude a telescope can detect, depend on aperture, exposure time, pixel size, and background noise. Professional observatories can push to very faint magnitudes. Amateur telescopes typically can't. But image stacking, combining multiple short exposures to reduce noise, can extend an amateur instrument's reach. If independent observers stacked dozens or hundreds of coronagraph frames, they might pull a faint signal out of the noise that wouldn't be visible in a single frame. Calibration matters too. Professional telescopes are meticulously calibrated. They know their 0-point magnitudes, their extinction coefficients, their systematic errors. Amateur stacks might not have that rigor. A brightness spike in an amateur image could be real, or it could be a calibration artifact, a hot pixel, a cosmic ray, a satellite trail. Without knowing the processing pipeline, it's hard to judge. But here's the thing. Multiple independent observers, using different instruments, different stacking methods, different software, reported similar findings. That redundancy suggests the signal is real, not an artifact of one person's processing choices. It's possible they're all making the same mistake, all misidentifying the same kind of noise, but it's less likely than the alternative, which is that they're detecting a real object that NASA's public messaging undersold. The phrase, "behind the sun," carries an implicit finality. It suggests the object is gone, out of reach, invisible. But astronomically, that's rarely true in an absolute sense. Objects in conjunction are harder to observe, yes. They require specialized instruments, non-standard viewing platforms, or patience to wait for better geometry. But harder is not impossible. And when NASA uses language that implies impossibility, they set themselves up for the charge of misdirection when alternate observations surface. Diagram time. Imagine the Sun at the center. Earth is orbiting at 1 astronomical unit. 3i Atlas is approaching from interstellar space, diving toward the Sun, reaching perihelion at 1.4 astronomical units. As it approaches, the angle between Earth, the Sun, and 3i Atlas shrinks. When that angle, the elongation, drops below a certain threshold, Earth-based telescopes lose visibility. But Mars, orbiting at 1.5 astronomical units and at a different orbital phase, has a different angle. From Mars, the elongation might still be large enough for observation. Similarly, a space-based coronagraph looking outward from near Earth can see past the suns, glare into regions that ground-based scopes can't. NASA's messaging focused on the Earth-based perspective because that's where most observers are, but by not clarifying that alternate platforms might maintain visibility, they created an impression of total blackout. And when independent observers using those alternate data sources reported findings, it looked like NASA had concealed possibilities. Scattering angles matter too. Light reflecting off cometary dust scatters in specific patterns depending on the phase angle, the angle between the Sun, the object, and the observer. At certain phase angles, scattering efficiency increases, making the object brighter than you'd predict from distance alone. If 3i Atlas happened to hit a favourable scattering geometry during conjunction, it could have appeared brighter in coronagraph images than simple inverse square law calculations would suggest. That could explain some of the brightness reports without invoking unusual activity. Noise levels, cosmic ray hits, detector saturation, blooming from bright nearby sources, all introduce uncertainty. Professional astronomers spend careers learning to distinguish signal from artifact. Amateurs often lack that training, but they compensate with enthusiasm, redundancy, and crowdsourced validation. When a finding gets replicated across multiple users, multiple instruments, and multiple processing methods, it gains credibility even if individual images are noisy. The critical takeaway is this: behind the Sun is observational shorthand, not absolute truth. Geometry limits visibility, but doesn't eliminate it for all instruments and all platforms. NASA's framing was accurate for a narrow context, Earth-based conventional telescopes, but incomplete for the broader observational ecosystem, and that incompleteness left space for independent observers to fill the gap and for skepticism to take root. If geometry allowed alternate observations, as it clearly did, then why didn't NASA's public messaging make that clearer? Was it an oversight? Or was it a framing choice designed to manage public attention? Because either answer has implications for trust. Part 7. Could it be non-natural? Hypotheses beyond cometary outgassing. Now we wade into speculative territory. Let's be clear from the start. There is no definitive evidence that 3i Atlas is artificial. None. Every observation so far can be explained, with varying degrees of comfort, by natural cometary processes. But the accumulation of oddities, the carbon dioxide dominance, the polarization extremes, the disputed brightness during conjunction, the jet orientation claims, raises a question that science is supposed to ask, even when the answer seems unlikely. What if this isn't just a comet? Avi Loeb has spent years arguing that we should take the possibility of interstellar probes or artifacts seriously. His analysis of Oumuamua suggested it might have been a light sail, a thin reflective structure accelerated by solar radiation pressure. The scientific community largely rejected that interpretation, favouring natural explanations like outgassing of hydrogen or nitrogen ices. But Loeb's broader point stands. If we're searching for extraterrestrial intelligence, we should be looking not just for radio signals, but for physical objects, probes, derelicts, anything that exhibits behavior incompatible with natural processes. He proposed a framework, informally called the Loeb scale, for assessing technosignatures in observed objects. The scale considers deviation from predicted motion, unusual material composition, geometric regularity, controlled orientation, and non-random behavior. 3i Atlas hasn't been formally evaluated on this scale, but let's walk through the criteria. Deviation from predicted motion. So far, no confirmed deviation from predicted motion. So far, no confirmed measurement exists showing 3i Atlas strayed from its gravitationally predicted path beyond what outgassing could explain. But the key phrase is "so far." If post-conjunction observations in December reveal trajectory deviations that can't be reconciled with the measured outgassing rates, that would be significant. Cometary non-gravitational acceleration is proportional to mass loss. If the object moved in ways that require more thrust than the observed dust and gas production could provide, you'd have a mismatch requiring explanation. Unusual material composition. Check. The carbon dioxide dominance is unusual but not impossible. It suggests formation in an extremely cold environment, colder than the regions where our solar system's comets formed. That could indicate an origin in a low metallicity star system, a system formed from primordial gas with fewer heavy elements. Or it could mean the object spent billions of years in interstellar space, cold enough to retain volatile carbon dioxide while losing lighter elements. Natural explanations exist, but they require specific formation conditions that are uncommon. Geometric regularity. We don't have high-resolution images of the nucleus. Hubble constrained the size but couldn't resolve the shape. If future observations reveal an elongated or faceted structure, something too regular to be natural erosion, that would raise flags. Oumuamua was estimated to be highly elongated, roughly 10:1 aspect ratio, which is unusual but not impossible for natural bodies. If 3i Atlas shows similar or more extreme geometry, the artificial artifact hypothesis gains plausibility. Controlled orientation. The disputed reports of sunward jets would fit here. If the jets are real, and if they're oriented in ways that produce thrust in specific directions, that could indicate control. But jet orientation can vary naturally based on rotation and the distribution of active areas on the nucleus. You'd need to show the orientation is non-random, that it persists in a way that produces a net acceleration in a preferred direction. That's hard to prove without continuous monitoring, which we didn't have during conjunction. Non-random behavior. This is the hardest to assess. Randomness versus intent requires statistical analysis over time. One brightness spike is an event. Multiple brightness spikes at regular intervals or correlated with specific orbital positions start to look like a pattern. If 3i Atlas exhibits pulsed activity, repeating on a schedule that doesn't correlate with solar heating or rotation, that would be anomalous, but we don't have that data yet. So where does 3i Atlas score on the Loeb scale? Probably low to moderate. It has some unusual properties, but none that definitively rule out natural processes. It's in the worth watching closely category, not the this is definitely artificial category. But that could change with more data. Let's entertain a scenario. Suppose 3i Atlas is an engineered object, a probe from another civilization. What would it be doing here? One possibility is an Oberth maneuver, a technique where you fire a rocket or expel mass at the point of highest velocity and closest approach to a massive body to maximize energy gain. For a spacecraft, performing an Oberth maneuver near the Sun could provide a gravity assist combined with a propulsive boost, allowing significant trajectory changes with minimal propellant. If 3i Atlas were using its perihelion passage to harvest energy from the Sun, perhaps through some kind of thermal conversion or photovoltaic system, and then expelling material to adjust its trajectory that could explain the anomalous jet reports, the sunward jets could be attitude control thrusters, orienting the object for maximum solar exposure or aligning it for the next phase of its mission. Speculative? Yes. Impossible? No. Another scenario involves passive monitoring. Maybe the object isn't actively maneuvering at all. Maybe it's a derelict, an ancient probe that lost control eons ago, but still exhibits residual activity from onboard systems degrading. The brightness spikes could be power surges from failing equipment. The unusual composition could be synthetic materials breaking down. The trajectory could be a result of a maneuver performed thousands or millions of years ago, and we're just seeing the inert remnant coasting through. Or maybe it's fully operational and deliberately avoiding detection. If an advanced civilization wanted to study our solar system, Without revealing their presence, they might design probes that mimic natural comets. They'd use outgassing to mask thruster activity. They'd maintain orbits that look gravitationally natural. They'd time their maneuvers during periods when observation is difficult, like solar conjunction, knowing that any anomalies would be attributed to noise or dismissed as amateur misinterpretation. That last scenario borders on conspiracy thinking, but it's not inherently absurd. If we were designing an interstellar probe to study another star system, we'd probably try to minimize our observational footprint. We'd want data without interference. We'd use natural cover. And if our probe were discovered, we'd hope the host civilization would assume it was natural unless the evidence became overwhelming. The problem with all these scenarios is they require attributing intent without evidence of intent. Every observation of 3i Atlas can be explained by natural processes, even if those explanations require invoking unusual but plausible conditions. The carbon dioxide dominance, explained by cold formation environment. The polarization, explained by unusual dust properties. The brightness during conjunction, explained by favourable scattering geometry or observer artifacts. The jets, explained by rotation and heterogeneous surface activity. You don't need artificial intelligence, you just need an exotic but natural comet. Occam's razor favours the natural explanation. The simplest hypothesis that fits the data is usually correct. But Occam's razor is a heuristic, not a law. Sometimes reality is complicated, sometimes the simple explanation is wrong. And in the case of interstellar visitors, we have a sample size of 3. Oumuamua was weird enough to generate serious scientific debate about artificial origins. Borisov looked like a normal comet. 3i Atlas is somewhere in between. Weird enough to be interesting, but not weird enough to be definitive. The honest answer is we don't know. We won't know until we get more data. And the way to get more data is to keep watching, keep measuring, keep asking uncomfortable questions. Because if 3i Atlas is natural, understanding its weirdness teaches us about the diversity of objects in the galaxy. And if it's artificial, well, that changes everything. The existence of even one confirmed technosignature, one object that cannot be explained by natural processes, would prove we're not alone. It would validate decades of SETI research. It would reframe humanity's place in the cosmos. So we watch. We wait. We resist the urge to conclude prematurely. We hold the tension between skepticism and openness. We demand evidence, but we don't dismiss possibilities just because they're uncomfortable, because the universe is under no obligation to make sense to us. And sometimes the most extraordinary discoveries begin with a single anomalous data point that everyone else ignored. Part 8. Institutional Trust, Transparency and Science Politics Interface. Let's zoom out. 3i Atlas is one object, but it's part of a larger conversation about how scientific institutions communicate with the public, how they manage uncertainty, and how they respond when outsiders challenge their narratives. This conversation isn't new. It's been building for years, maybe decades, as the democratization of information collides with the traditional gatekeeping role of experts. Think back to Oumuamua. October 2017, the first confirmed interstellar visitor. Elongated, tumbling, accelerating away from the sun in a way that couldn't be explained by gravity alone. The scientific community proposed several natural explanations. Outgassing of volatile ices, even though no coma was detected. A hydrogen iceberg, even though hydrogen ice shouldn't survive in interstellar space. A nitrogen ice fragment from a Pluto-like exoplanet, even though the statistics of such fragments entering our solar system are vanishingly small. Avi Loeb suggested maybe it was artificial, a light sail or debris from one. The reaction from the astronomical community was swift and largely negative. Loeb was accused of seeking attention, of damaging the credibility of serious science, of invoking aliens prematurely. But he countered that we should be open to all possibilities, that dismissing artificial explanations a priori is itself unscientific. The debate played out in journals, in conferences, in the media, and the public watched, fascinated, as scientists argued about something that sounded like science fiction. NASA's role in that debate was measured. They didn't endorse Loeb's hypothesis, but they didn't completely shut it down either. They released data. They encouraged further observation, though Oumuamua was already too far away for follow-up. They acknowledged the anomalies while favouring natural explanations. It was a balancing act, maintaining credibility while not appearing close-minded. Now compare that to 3i Atlas. The anomalies are less dramatic than Oumuamua, but still present. The public interest is growing. The independent observers are more organised, more vocal. And NASA's response has been quieter. Fewer press releases, less engagement with alternative claims, more reliance on the wait-and-see approach. Is that because the data is less compelling? Or because they learned from Oumuamua that engaging with speculation generates more questions than answers? There's a tension here between scientific caution and public transparency. Scientists are trained to wait for peer review, to avoid over-interpreting preliminary data, to hedge their conclusions with uncertainty. But the public wants answers now. They want to know what's happening in their sky. They don't want to wait 6 months for a paper to clear peer review. And when institutions prioritise caution over communication, the vacuum gets filled with speculation, some of it reasonable, some of it not. The phrase "behind the sun" is a case study in how framing shapes perception. To an astronomer, it's jargon for solar conjunction limits visibility. To the public, it sounds like the object is hidden and we can't talk about it. NASA probably didn't intend the second interpretation, but that's what many people heard. And when independent observers started posting images claiming to show the object during the hidden period, it looked like NASA had been caught in a mismatch between their framing and reality. Was that intentional misdirection? Almost certainly not. More likely, it was a communication choice prioritizing simplicity over precision. NASA wanted to tell the public, "You won't be able to see this for a few months, so don't waste your time looking." They used accessible language to convey that message. They didn't anticipate that some people would interpret "you won't be able to see it" as "it's not visible to anyone," or that alternate observation platforms would generate data contradicting the simplified narrative. But in an era of citizen science, those oversimplifications become vulnerabilities. Because someone will always check, someone will always pull the coronagraph data, stack the frames, cross-reference the timestamps, and if what they find doesn't match what they were told, trust erodes. This isn't unique to NASA, it's a broader challenge for all scientific institutions. How do you communicate complex, uncertain information to a public that wants clarity? How do you maintain authority when anyone with an internet connection can access raw data and draw their own conclusions? How do you respond to challenges from non-experts who lack formal training but sometimes spot things professionals miss? Some institutions respond by doubling down on gatekeeping. Only peer-reviewed findings are legitimate. Only credentialed scientists can make authoritative claims. Amateur contributions are welcome but must be vetted through official channels. That approach preserves credibility, but risks alienating the very people who could be valuable collaborators. Other institutions embrace openness. They release data quickly. They engage with amateur findings publicly. They acknowledge uncertainty and invite scrutiny. That approach builds trust, but risks being overwhelmed by the volume of claims, many of which turn out to be artifacts or misunderstandings. NASA tries to walk a middle path. They release data through archives accessible to the public. They participate in forums and conferences where amateurs present findings, but they also maintain standards for what counts as confirmed, what gets elevated to official communication. And sometimes that middle path satisfies no one. Professionals think they're too accommodating of amateur speculation. Amateurs think they're too dismissive of citizen contributions. The 3i Atlas situation might force a recalibration. If the independent observer claims are vindicated, if December observations confirm that anomalies were real and that alternate instruments did maintain visibility during conjunction, NASA will face questions about why they didn't communicate those possibilities more clearly. They'll be accused of oversimplification at best, narrative control at worst. If the independent claims turn out to be artifacts or misinterpretations, NASA will still face questions about why they didn't engage more actively to clarify. Silence in the face of growing speculation can look like dismissiveness or evasion, even when it's just patience. There's a philosophical dimension here too. Who owns the sky? Who has the right to interpret what's observed? In one sense, the sky belongs to everyone. Anyone can look up. Anyone can point a telescope. Anyone can analyze data. But interpretation requires expertise, context, understanding of systematic errors and calibration, and the limitations of instruments. So does that mean only experts should make public claims? Or does it mean we need better frameworks for integrating amateur contributions into professional discourse? 3i Atlas won't answer those questions definitively, but it's a data point in an ongoing evolution of how science communicates with society, and the outcome will shape how future anomalies, future interstellar visitors, future discoveries are handled. Because the next time something strange appears in our sky, and there will be a next time, both institutions and individuals will remember how this situation played out. They'll remember what worked and what didn't. They'll adjust, and hopefully we'll move toward a model where transparency and rigor coexist, where amateurs and professionals collaborate rather than clash, where the public can trust that they're getting the full picture even when that picture is uncertain. Part 9. Community response and data verification efforts. While NASA stayed quiet, the internet did what the internet does. It mobilized. Within days of the first independent observer posts claiming visibility during conjunction, astronomy forums lit up. Reddit threads on communities like space and astronomy, and even conspiracy began tracking 3i Atlas. Discord servers dedicated to citizen astronomy shared raw data files. Users compared notes, cross-referenced orbital elements, debated processing methods. One prominent post on a forum detailed a user's attempt to stack GOES coronagraph frames. They downloaded hundreds of images covering the perihelion window, registered them using star positions, applied noise reduction, and looked for persistent signals. The result was a faint but detectable brightening in the expected position of 3i Atlas. The user posted their methodology, their software settings, their source files. Others tried to replicate it. Some succeeded. Some got noise. The debate became a collective verification effort. Another user focused on Mars. They scraped the publicly available Perseverance rover image archive, looking for sky-facing shots taken during the early October flyby window. Most images were surface geology, rocks and sand and distant mountains. But a handful pointed upward, calibration frames or navigation checks. In those images, after heavy enhancement, the user claimed to see a faint streak consistent with a fast-moving object. They calculated expected position based on the published orbital elements. The match was close, but not perfect. Close enough to be interesting, not perfect enough to be certain. The strengths of this community effort are obvious. Redundancy. When multiple people using different methods arrive at similar conclusions, confidence increases. Transparency. The data and methods are shared openly, inviting scrutiny and replication. Speed. These posts appeared within days of perihelion, faster than any peer-reviewed paper could, and diversity. The community includes retired engineers, amateur astronomers with decades of experience, software developers, students, people from all over the world contributing different perspectives. But the weaknesses are equally obvious: calibration uncertainty. Amateur image processing doesn't always account for systematic errors, flat fielding, dark frame subtraction, bias corrections. A bright pixel could be signal, or it could be a hot pixel that wasn't properly masked. Confirmation bias. If you're looking for an anomaly, you might interpret ambiguous data as supporting that anomaly. Selection bias. Maybe dozens of people tried the same stacking procedure and got nothing, but only the ones who saw something posted their results. Timestamp ambiguity is another issue. Space instrument data often comes with metadata indicating observation time, but not always in user-friendly formats. UTC versus local time versus spacecraft time can cause confusion. If an independent observer misdates an image by even a few hours, their claimed detection during conjunction might actually be from before or after the critical window. Frame registration, aligning multiple images so that stars overlap perfectly, is non-trivial. If your registration is off by even a pixel or two, stacking introduces artifacts. Those artifacts can look like faint moving objects. Professional astronomers use sophisticated registration algorithms and validate them against known star positions. Amateurs might use simpler tools that work most of the time but fail in edge cases. Despite these limitations, the community efforts have value. They act as a distributed verification network. They catch things that might slip through institutional processes. They ask questions that professionals might not think to ask, and they create a public record that persists even if official channels go silent. One group tried to formalize the process. They set up a shared spreadsheet where users could log their detection attempts, including observation date, instrument used, processing method, and result. The goal was to aggregate enough attempts to assess whether the signal was real or whether it was artifact-prone processing. As of early November, the spreadsheet had over 50 entries. About 30 claimed positive detection. 20 reported noise or null results. That's a 60% success rate, which is intriguing but not definitive. The null results are important. They suggest that detecting 3i Atlas during conjunction isn't trivial, that it requires either good data or good processing or both. If everyone who tried succeeded easily, that would strengthen the claim. If only a few succeeded, it might mean those few got lucky with artifacts. The reality, 60% success, sits in the uncertain middle. Some community members pushed for official data release. They filed Freedom of Information Act requests asking for any Mars orbiter images of 3i Atlas. They contacted NASA's Planetary Data System, asking about observation schedules for the Mars Reconnaissance Orbiter during early October. They reached out to the Soho Science team asking if coronagraph data showing the object would be archived and when it would be public. The responses were mixed. The Planetary Data System confirmed that Perseverance images are publicly archived, but noted that not all images are processed immediately. High-priority science targets get processed first. Sky calibration frames might take months. The Soho team confirmed that coronagraph data is public and archived, but cautioned that interpreting faint signals in solar images requires expertise. They didn't confirm or deny whether 3i Atlas appeared in their data. NASA's silence on these requests isn't necessarily suspicious. Large institutions have bureaucratic processes, data requests take time, and confirming or denying detections in noisy data requires analysis that can't be done in a few days. But from the community's perspective, the silence feels like stonewalling. They have images they think show the object. They want official validation or refutation. They're not getting either. This dynamic, the tension between community urgency and institutional caution, defines modern citizen science. The community wants to contribute. They want to be taken seriously. They want their findings integrated into the professional narrative, but they also sometimes overestimate the certainty of their conclusions. They underappreciate the complexity of verification. They assume that because they see something, it must be real, without fully accounting for the ways instruments and processing can deceive. Professional astronomers, for their part, sometimes underestimate the capability and diligence of amateurs. They assume amateur data is low quality, that amateur conclusions are premature. They don't always engage with amateur findings promptly or respectfully, and that creates resentment, the sense that institutions are gatekeeping knowledge rather than collaborating to expand it. The ideal outcome would be partnership. Amateurs flag interesting signals. Professionals follow up with higher quality instruments and rigorous analysis. Findings are published collaboratively, with credit shared. That happens sometimes. Supernovae discoveries, asteroid detections, variable star monitoring all benefit from amateur contributions. But when the subject is controversial, when the stakes involve potential paradigm shifts like artificial interstellar objects, the collaboration breaks down. Professionals become defensive, amateurs become aggressive, and the data, the actual observations that should be the focus, get lost in the noise. 3i Atlas might be a turning point. If the community-generated data holds up, if December observations confirm what independents claim to see during conjunction, then institutions will have to acknowledge that the distributed verification network works, that citizen science isn't just hobbyism, that sometimes the outsiders see what the insiders miss. And that might lead to better frameworks for integrating amateur contributions, faster data release, more transparency. Or it might not. If the community claims turn out to be artifacts, if professional follow-up finds nothing anomalous, the lesson will be different. It'll be a reminder that verification is hard, that expertise matters, that seeing isn't always believing. Either way, the effort itself is valuable, because asking questions, even when the answers are uncertain, is how science moves forward. Part 10. Forecasting what happens after conjunction. December is the key. According to NASA's published timeline, 3i Atlas should become observable again in early to mid-December as it moves away from the Sun and the elongation angle increases. Ground-based telescopes in the southern hemisphere will have the best view initially. The object will appear in pre-dawn skies, low on the horizon, gradually climbing higher as days pass. Professional observatories have already filed observation requests. The Hubble Space Telescope is scheduled for follow-up imaging, attempting to resolve the nucleus and measure any changes in size or activity since the pre-conjunction observations. The James Webb Space Telescope might get another slot, depending on target of opportunity scheduling and competing priorities. Ground-based facilities like the Very Large Telescope in Chile and the Keck Observatory in Hawaii have expressed interest, assuming the object is bright enough and positioned favourably. The scientific goals are clear. First, confirm the trajectory. Did 3i Atlas follow the predicted orbit, or were there deviations? Even small deviations, fractions of a degree or slight changes in velocity, would be significant. They'd indicate non-gravitational forces, either from outgassing or, in the more speculative scenarios, from active manoeuvring. Precise astrometry, measuring the object's position against background stars, will be critical. Second, characterize the activity. Is the comet still producing a coma? Has the dust production rate increased, decreased, or stayed constant? Are there new jets, or have existing jets changed orientation? Spectroscopy will reveal the composition of the outgassing material. If the carbon dioxide dominance persists, that supports the cold formation hypothesis. If water vapour suddenly appears, that might indicate subsurface layers being exposed as the outer layers erode. Third, monitor the brightness. Comets typically brighten as they approach the Sun and fade as they recede, following a predictable power law. If 3i Atlas deviates from that curve, if it brightens unexpectedly or fades too quickly, that would require explanation. Photometry, measuring brightness over time, will track the light curve and compare it to models. Fourth, look for fragmentation. Comets sometimes break apart during close solar approaches due to thermal stress or tidal forces. If 3i Atlas fragmented near perihelion, we'd see multiple components separating from the main nucleus. That could explain some of the brightness anomalies, sudden increases from fresh icy surfaces being exposed. Imaging will search for fragments. Fifth, refine the composition. Beyond just carbon dioxide and water, what else is present? Methane, ammonia, organic compounds, silicates, metals. Each element or molecule tells a story about where and how the object formed. Spectroscopic surveys across multiple wavelengths will build a comprehensive inventory. Amateur astronomers will play a role too. Backyard telescopes can't match professional resolution or sensitivity, but they can monitor brightness continuously, catching short-term variations that scheduled professional observations might miss. Amateurs can alert professionals to sudden outbursts or unexpected changes, triggering target of opportunity follow-up, and amateurs can provide the redundancy, the multiple independent measurements that confirm findings aren't instrumental artifacts. What should we watch for? Several possibilities, ranging from benign to paradigm shifting. On the benign end, 3i Atlas reappears exactly as predicted. The trajectory matches. The brightness follows the expected curve. The activity is consistent with standard cometary outgassing. The anomalies reported during conjunction are explained as artifacts or viewing geometry effects. NASA's narrative is vindicated. The independent observers acknowledge they misinterpreted noisy data. The story ends with a collective shrug and a reminder that not every anomaly is a mystery. On the more interesting end, deviations appear. The trajectory is slightly off, requiring non-gravitational acceleration beyond what the observed outgassing can provide. The brightness is higher or lower than predicted, suggesting activity changes during the unobserved perihelion passage. New jets appear or existing jets have reoriented in ways that don't correlate with simple rotation. The composition shows unexpected elements or ratios that challenge formation models. These findings wouldn't prove artificiality, but they deepen the mystery, justifying more attention and more resources for follow-up. On the speculative extreme, something truly weird happens. The object doesn't reappear where predicted, implying a significant trajectory change. The brightness exhibits pulsed behavior, repeating on a regular schedule inconsistent with thermal or rotational cycles. The spectroscopy reveals signatures inconsistent with natural materials, perhaps narrow emission lines suggesting refined elements, or isotope ratios incompatible with stellar nucleosynthesis. High-resolution imaging reveals geometric structures, faceted surfaces, or regular patterns. These findings would catapult 3i Atlas into the category of potential technosignature, demanding exhaustive verification and follow-up. The most likely outcome is somewhere between benign and interesting. Some anomalies will persist, others will resolve. The scientific community will debate interpretations. Papers will be published arguing both natural and exotic explanations. The public will remain divided between those convinced NASA is hiding something and those convinced the whole controversy is much ado about nothing. And 3i Atlas will continue its journey out of the solar system, gradually fading, eventually becoming too faint for even the largest telescopes to track. But here's the suspense. We don't know yet. December is weeks away. The observations haven't been made. The data hasn't been analysed. Right now, at this moment, 3i Atlas exists in a superposition of possibilities. It's both a mundane comet and a potential artifact. It's both vindication and embarrassment for NASA. It's both confirmation and refutation of independent observer claims. And we won't collapse that superposition until the measurements come in. So we wait, we prepare, we discuss, we speculate responsibly. We remind ourselves that extraordinary claims require extraordinary evidence, and that the null hypothesis, the boring natural explanation, is usually correct. But we also remind ourselves that the universe has surprised us before, that sometimes the boring explanation is wrong, that sometimes the thing everyone dismissed as noise turns out to be signal, and that the only way to find out is to keep watching, keep measuring, keep asking whether what we're seeing is what we think we're seeing. December will be revealing, not just about 3i Atlas, but about how science handles uncertainty, how institutions and citizen scientists collaborate or conflict, how humanity responds when something in the sky doesn't quite make sense. The object itself is fascinating, but the process, the way we grapple with the unknown, might be even more important. Because 3i Atlas is just one visitor. There will be others, and how we handle this one sets the precedent for all the ones to come. Part 11. James Webb Space Telescope Latest Discovery. While 3i Atlas dominates the interstellar visitor conversation, the James Webb Space Telescope has been busy rewriting other chapters of astronomy. In September 2025, Webb released data on an exoplanet atmosphere that nobody expected. The planet, designated K218b, orbits a red dwarf star about 120 light-years away. It's in the habitable zone, the region where liquid water could exist on the surface. Previous observations from Hubble and other telescopes had detected water vapor in its atmosphere, which was exciting but not shocking. Webb went deeper. Its near-infrared spectrograph detected not just water vapor, but also dimethyl sulfide, a molecule that on Earth is produced almost exclusively by biological processes, specifically by marine phytoplankton. Finding it in an exoplanet atmosphere raised immediate questions. Is this a biosignature? Is K218b hosting life? The scientific community's response was cautious. Dimethyl sulfide can be produced abiotically through photochemical reactions involving sulfur compounds and methane. The detection was at the edge of Webb's sensitivity, requiring careful analysis to rule out instrumental artifacts or contamination from other molecules with similar spectral signatures. Multiple teams rushed to model whether non-biological chemistry could explain the observations. Some said yes, it's possible through exotic atmospheric reactions. Others said the abundance is hard to explain without biology. The parallels to 3i Atlas are striking. In both cases, an observation challenges expectations. In both cases, natural explanations exist but require invoking unusual conditions. In both cases, the more exciting interpretation, life on K218b, artificiality for 3i Atlas, remains speculative pending more data. And in both cases, institutions are walking a tightrope between reporting findings and avoiding premature conclusions. NASA's communication about K218b was measured. They published the data. They acknowledged the dimethyl sulfide detection. They emphasized that more observations are needed to confirm and that alternative explanations must be ruled out. They didn't declare, "we found alien life," but they also didn't dismiss the possibility. It was a masterclass in scientific caution, acknowledging excitement while managing expectations. Compare that to the 3i Atlas messaging: minimal updates, limited engagement with anomaly claims, emphasis on the blackout period rather than the scientific intrigue. The difference might be strategic. Exoplanet atmospheres are distant, abstract, non-threatening. Interstellar visitors are in our solar system, closer, more immediate. Maybe NASA judges that the public can handle speculation about life on a distant exoplanet, but gets too anxious about potential artifacts nearby. Or maybe the difference is evidentiary. The K218b detection, while requiring confirmation, is at least based on professional peer-reviewed telescope data. The 3I Atlas anomalies, as reported by independents, are based on amateur processing of publicly available but not scientifically vetted images. It's easier to engage with the former than the latter. Either way, the K218b situation offers lessons. Transparency builds trust. NASA released the web, data quickly. They hosted press briefings. They invited questions. They acknowledged uncertainty while providing context. That openness didn't eliminate speculation. People are already arguing about whether we've detected alien microbes, but it did ensure the speculation was informed. People had access to the actual spectra, the error bars, the alternative models. They could make up their own minds based on real information. The 3I Atlas situation lacks that transparency. The independent observer claims aren't being addressed publicly. The alternate instrument data isn't being contextualized by NASA. The vacuum is being filled by speculation, some informed, some not. And that erodes trust in ways that transparency, even uncomfortable transparency, wouldn't. There's a broader point here about how institutions handle surprises. Space science is full of them. Every time we point a new instrument at the sky, we see something unexpected. Sometimes it's a minor puzzle, easily explained. Sometimes it's a major challenge to existing models. And occasionally it's something that forces a paradigm shift, that changes how we understand the universe. The history of astronomy is a history of revising expectations. We thought the universe was static, then we discovered expansion. We thought galaxies were the largest structures, then we found superclusters and cosmic filaments. We thought planets were rare, then we discovered thousands of exoplanets. We thought fast radio bursts were instrumental glitches, then we confirmed they were astrophysical. Each surprise required institutions to acknowledge they were wrong, to update their models, to communicate revised understanding to the public. 3I Atlas and K218b are current chapters in that ongoing story. Both involve observations that don't fit neatly into existing boxes. Both require patience, more data, careful analysis. Both tempt us with extraordinary implications while demanding we remain skeptical. And both test whether institutions can navigate the space between premature certainty and endless agnosticism. The outcome for K218b won't be known for years. Webb is scheduled for follow-up observations. Other telescopes will join the effort. Models will improve. Eventually we'll have enough data to say whether dimethyl sulfide is likely biological or likely abiotic. Until then, we hold the possibility in mind without committing to it as fact. The same applies to 3I Atlas. December observations will add data. Analysis will improve. Models will be refined. And eventually we'll know whether the anomalies were real or imagined, whether the object was exotic or mundane. Until then, we watch and we wait, reminded that the universe doesn't reveal its secrets quickly and that the process of discovery is often messier and longer than we'd like. Part 12. AI-driven asteroid and comet detection breakthrough. In August 2025, a team at the University of Washington announced a breakthrough in automated sky surveys. They developed a machine learning algorithm trained on millions of telescope images to detect asteroids and comets that traditional detection pipelines missed. The algorithm looked for patterns of motion, brightness variations, and morphological features that indicated solar system objects rather than stars or galaxies. The results were impressive. In a test run analyzing archived data from the Zwicky Transient Facility, a sky survey telescope in California, the algorithm flagged over 300 candidate objects that the standard pipeline had overlooked. Follow-up confirmed that 90% were real, either previously uncatalogued asteroids or known objects whose positions weren't updated. 10% were artifacts or misclassifications, an acceptable error rate for a new system. But one detection stood out. The algorithm flagged an object in images from June 2025 that hadn't been identified by human analysts or the standard automated pipeline. The object was faint, near the detection limit, and moved slowly, consistent with a distant comet or a Kuiper Belt object. Closer inspection revealed it was an interstellar visitor, later confirmed as 3I Atlas, after its official discovery in July by the Atlas survey. Wait. The machine learning algorithm detected 3I Atlas before the official discovery? That's the claim the team made in their preprint paper. They argued their algorithm identified the object in June images, but that the detection wasn't flagged for human review until after Atlas announced the discovery in July. The delay was due to the volume of candidates the algorithm generated and the limited resources for follow-up. This revelation raised questions. If AI spotted 3I Atlas earlier than officially reported, what else might AI spot that humans miss? And could AI have detected anomalies during the conjunction period that human-led analysis didn't pursue? The University of Washington team proposed retrospectively analyzing coronagraph and Mars orbiter data, using their algorithm to search for 3I Atlas during the blackout window. They argued that machine learning excels at finding faint signals in noisy data, exactly the challenge independent observers faced when stacking frames. If the algorithm confirmed detections during conjunction, that would validate the independent claims. If it found nothing, that would suggest the independent detections were artifacts. As of early November, the team was still negotiating access to the necessary data archives. Coronagraph data is publicly available but voluminous and not formatted for easy machine learning ingestion. Mars orbiter data requires permissions from various NASA divisions. The bureaucratic wheels turn slowly, but the proposal highlights a broader shift in astronomy. Algorithms are becoming co-discoverers, not just tools. They don't process data according to human-defined rules. They learn patterns, identify anomalies, make predictions that humans might not think to test. And as they improve, they challenge the traditional workflow where humans decide what's interesting and what to investigate. This matters for objects like 3I Atlas because human attention is limited and biased. We look where we expect to find things. We prioritize bright objects over faint ones. We focus on regions of sky with historical interest. AI doesn't have those biases. It treats every pixel, every frame, every data point with equal scrutiny. It finds things in the margins, in the noise, in the places we didn't think to look. The flip side is that AI can be fooled. It can learn patterns that aren't real, artifacts of the training data or the imaging system. It can flag hot pixels as asteroids, cosmic rays as comets, satellite trails as interstellar visitors. That's why the 10% false positive rate in the University of Washington study is both impressive and concerning. 90% accuracy is excellent for a new system, but 10% false positives means that for every 10 detections, one is wrong. Scale that to millions of images and you get thousands of false alarms. Human review remains essential, but the workflow shifts. Instead of humans analyzing every image and occasionally missing something, AI analyzes every image, and humans review the candidate's AI flags. That's faster, more comprehensive, and less prone to human oversight. But it also means we're trusting algorithms to decide what deserves attention. For 3I Atlas, an AI audit could settle some controversies. If machine learning consistently detects the object in conjunction period data across multiple instruments, that's strong evidence the signal is real. If it finds nothing or only sporadic detections that don't correlate, that suggests the independent observer claims were artifacts. The beauty of AI is its replicability. Run the same algorithm on the same data and you get the same result. No human subjectivity, no confirmation bias, just pattern recognition. But there's a philosophical dimension too. If AI discovers something humans missed, who gets credit? Does the algorithm's creator get credit for enabling the discovery? Does the institution that collected the data? Does the person who first suspected the anomaly and prompted the AI investigation? In traditional science, discovery credit is straightforward. The person who first observes and reports gets credit. But in AI-assisted science, the discovery process is distributed across humans and machines in ways that blur attribution. The 3I Atlas controversy might be an early test case. If AI validates independent observer detections, does that vindicate the observers even though they were initially dismissed? Or does it just vindicate the algorithm? And if NASA eventually acknowledges anomalies that AI flagged but official channels didn't emphasize, how does that reshape the narrative about institutional transparency? These questions don't have clear answers yet, but they're becoming urgent as AI tools proliferate across astronomy. We're entering an era where discoveries might come from algorithm analyzing archives of data collected years ago, where human astronomers are increasingly curators and interpreters rather than direct observers. That's not bad, it's evolution. But it requires rethinking how we validate findings, how we communicate uncertainty, and how we allocate credit in a human-machine partnership. The University of Washington team's proposal to audit 3i Atlas data with AI is elegant because it sidesteps human politics. The algorithm doesn't care about NASA's reputation or independent observers' credibility. It just looks for patterns. If the patterns are there, it reports them. If not, it says so. That objectivity is valuable in a controversy where emotions and institutional stakes run high. By December, we might have results. The AI audit might confirm, refute, or complicate the independent observer claims, and that outcome, whatever it is, will inform how the astronomical community integrates machine learning into the observational workflow. Because 3i Atlas is just one object, but the questions it raises about detection, verification, communication, and trust apply to everything we point our telescopes toward, and as AI becomes more capable, those questions become more pressing. Part 13. Solar Probe and Parker. Solar Probe findings. Let's talk about the Sun, because understanding what happens near the Sun matters for interpreting what happened to 3i Atlas during perihelion. The Parker Solar Probe, launched in 2018, has been diving closer to the Sun than any spacecraft in history. Its mission is to study the solar corona, the outer atmosphere, and to understand the solar wind, the stream of charged particles flowing outward from the Sun. In July 2025, Parker released data from its latest close approach, a perihelion pass that brought it within 4 million miles of the Sun's surface. The findings were surprising. The probe detected massive jets of plasma erupting from the corona, structures not seen in previous passes. These jets, some extending millions of miles into space, were driven by magnetic reconnection events where tangled magnetic field lines snap and release energy explosively. The jets weren't constant. They pulsed, appearing and disappearing on timescales of minutes to hours. They carried tremendous energy, accelerating particles to near relativistic speeds. And they altered the structure of the solar wind in their vicinity, creating turbulent regions where magnetic fields twisted and particle densities spiked. Why does this matter for 3i Atlas? Because the comet passed through the corona, or very close to it during perihelion on October 29th. If it encountered one of these plasma jets, the interaction could produce unusual brightness spikes, tail structure changes, or even trajectory perturbations. Cometary material interacting with a jet could ionize, glow, scatter light in unexpected ways. It could look anomalous without being anomalous. Parker's data also revealed that the solar wind near perihelion is more variable than models predicted. Magnetic field strength fluctuates wildly. Particle density changes by orders of magnitude over short distances. Radiation pressure, the force of sunlight pushing on dust particles, varies as magnetic structures focus or defocus the solar output. All of this introduces uncertainty into predictions of how a comet should behave near the Sun. The standard model assumes a smooth, steady solar wind and radiation field, but Parker showed that's an oversimplification. The near-solar environment is chaotic, dynamic, unpredictable. A comet in that environment might exhibit behaviors that look controlled or artificial, but are actually responses to external forces we didn't model correctly. This is relevant to the disputed sunward jets reported by independent observers. If 3i Atlas encountered a coronal plasma jet during perihelion, the interaction could deflect cometary material, making it appear to move sunward against radiation pressure. It's not that the comet is expelling material toward the Sun, it's that the plasma jet is pushing cometary material in unexpected directions, and from our vantage point it looks like a sunward jet. Similarly, the brightness anomalies could be explained by variable solar output. If magnetic reconnection events brightened localized regions of the corona, and 3i Atlas passed through or near those regions, the reflected and scattered light could make the comet appear brighter than predicted. Not because the comet itself increased activity, but because the illumination changed. Parker's findings complicate interpretation, which is both frustrating and valuable. Frustrating because it adds more variables, more unknowns, more possible explanations for anomalies. Valuable because it reminds us that the solar environment is more complex than our simplified models, and that extraordinary seeming observations might have ordinary causes if we account for that complexity. The Parker team is collaborating with comet researchers to model how objects like 3i Atlas interact with the dynamic near-solar environment revealed by the probe. Those models will take months to develop and validate, but once available, They'll provide a better baseline for assessing whether 3I Atlas behaved normally or anomalously. There's also a forward-looking aspect. Future interstellar visitors that pass close to the Sun will be interpreted in light of Parker's discoveries. We won't assume smooth conditions. We'll account for jets, turbulence, variable radiation. Our predictions will be better, and our ability to distinguish genuinely anomalous behavior from environmental response will improve. But for 3I Atlas, Parker's data arrives too late to fully inform the conjunction period analysis. The models aren't ready. The environmental conditions during October 29th haven't been reconstructed in detail, so we're left with uncertainty. The anomalies could be real, intrinsic to the object, or they could be artifacts of an unexpectedly dynamic solar environment. We won't know until the models mature and until post-conjunction observations provide comparison data. Parker Solar Probe reminds us that space isn't empty, and it isn't simple. The Sun influences everything in its vicinity in ways we're still discovering. And objects passing through that influenced region, like 3I Atlas, are subject to forces and interactions that we don't yet fully understand. That doesn't mean we give up on explanation. It means we build better models, gather more data, and remain humble about the limits of current knowledge. The December observations of 3I Atlas will be crucial for this modelling effort. If the object's behaviour after perihelion matches the updated models that include Parker's findings, that strengthens the case for natural explanation. If discrepancies persist even with the improved models, that moves the anomaly into more interesting territory. And if the post-perihelion behaviour is radically different from pre-perihelion, that suggests something significant happened during the close solar pass, something worth investigating deeply. The Sun is a laboratory we can't replicate on Earth. The magnetic fields, the plasma densities, the radiation intensities all exceed what we can produce in experiments. So we rely on probes like Parker to measure and spacecraft observing comets like 3I Atlas to interact with those conditions in ways that teach us. Every close solar pass by an object is an experiment, testing our understanding of solar physics and cometary physics simultaneously. 3I Atlas is one such experiment. Parker provides context, and together they push the boundaries of what we know about the most fundamental and most complex object in our solar system, the star that gives us life and light. Part 14. Breakthrough in dark matter and modified gravity constraints. In late September 2025, a collaboration of physicists analysing data from the Gaia Space Telescope published a paper that tightened constraints on modified gravity theories in the inner solar system. Gaia, a European Space Agency mission, measures the positions and motions of stars with extraordinary precision, but it also tracks asteroids, comets, and other solar system objects, and those measurements can be used to test whether gravity behaves exactly as Einstein's general relativity predicts, or whether subtle deviations exist. Modified gravity theories propose that at very low accelerations, far from massive bodies, or under other specific conditions, gravitational attraction differs from the inverse square law predicted by Newton and refined by Einstein. These theories were originally developed to explain galaxy rotation curves without invoking dark matter. If gravity is slightly stronger at large distances, galaxies could rotate faster than visible matter alone would allow, but modified gravity makes testable predictions in the solar system too. Specifically, it predicts tiny deviations in the orbits of planets, asteroids, and comets. Objects at the outer edge of the solar system, where accelerations are low, should experience slightly different gravitational forces than general relativity predicts. Those differences are small, parts per billion, but Gaia's precision is sufficient to detect them. The collaboration analysed Gaia's tracking of thousands of asteroids and several comets over multiple years. They looked for orbital anomalies, deviations from the predicted paths that couldn't be explained by gravitational interactions with known planets. They found nothing. No statistically significant deviations. The orbits matched general relativity's predictions to within measurement error. This result tightens the constraints on modified gravity. It doesn't rule out all versions of these theories, but it does rule out versions that predict detectable deviations in the inner and mid-solar system. If modified gravity effects exist, they must be smaller or more distant than current measurements can resolve. What does this have to do with 3I Atlas? Potentially a lot. If you're trying to explain trajectory deviations, you have two main options: non-gravitational forces like outgassing, or external factors like modified gravity or unknown perturbations. The Gaia result tells us that modified gravity is unlikely to explain any trajectory anomalies 3I Atlas might exhibit. If the object doesn't follow its predicted orbit, the explanation must be non-gravitational forces or errors in the prediction model. That narrows the possibilities. It means that if 3I Atlas showed controlled maneuvering, you can't attribute it to exotic physics affecting all objects in that region of space. You have to attribute it to something specific to 3I Atlas, either natural like outgassing, or unnatural like artificial propulsion. The Gaia findings also matter for interpreting speed measurements. Hyperbolic excess velocity, the speed an object has relative to the Sun after accounting for gravitational acceleration, should be constant for an interstellar visitor unless non-gravitational forces intervene. If 3I Atlas's velocity changed during its solar system passage beyond what outgassing predicts, modified gravity is now an unlikely explanation. You're left with either unmodelled natural forces or artificial control. Dark matter also enters the conversation. Some theories propose that dark matter particles accumulate near the Sun, creating a localized overdensity that could gravitationally influence passing objects. The Gaia result doesn't directly constrain this scenario because dark matter effects would be different from modified gravity effects. But it does establish that anything pulling or pushing on asteroids and comets near the Sun must be very subtle, below Gaia's detection threshold. If dark matter near the Sun were abundant enough to noticeably affect 3I Atlas, it should also affect the asteroids and comets Gaia tracked. Since Gaia didn't see anomalies, dark matter overdensity is unlikely to be a significant factor. Again, you're left with forces specific to 3I Atlas, not environmental factors affecting everything. This process of elimination is valuable. Each time a potential explanation is constrained or ruled out, the remaining possibilities become clearer. The Gaia findings don't tell us what 3I Atlas is, but they tell us what it isn't. It isn't being pulled by unmodelled gravitational effects. It isn't responding to exotic physics that pervades the inner solar system. If it's behaving strangely, the strangeness is intrinsic, localized to the object itself. That raises the stakes for December observations. If trajectory deviations appear and can't be explained by outgassing, we've run out of conventional explanations. Modified gravity, ruled out. Dark matter perturbations, unlikely. Gravitational interactions with unknown objects. Gaia would have detected those too. You're left with either dramatically better measurements of outgassing that somehow were missed earlier, or you're left with something that doesn't fit the natural framework. The broader context is that 2025 has been a year of constraint tightening across physics. The Gaia results, combined with Parker Solar Probe data, combined with improved comet models, combined with AI-enhanced detection algorithms, all narrow the space for unexplained phenomena. We're getting better at modelling reality, which means genuine anomalies stand out more clearly against the background of expected behaviour. 3I Atlas exists in that narrowing space. It's strange enough to be interesting, but not strange enough to be definitive. It sits right at the boundary between exotic but natural and genuinely anomalous. The Gaia findings push it slightly toward the latter category by eliminating one class of natural explanations. Parker's findings push it back toward the former by adding complexity to the solar environment. The result is a tension, an uncertainty that only more data can resolve, and that's where we are, on the edge of knowing. December approaches, telescopes prepare, models refine, and we wait to see which way the data falls, knowing that whatever we learn, the universe will still hold more mysteries than answers, because that's the nature of exploration. Every answer generates new questions, every constraint reveals new frontiers, and every object like 3I Atlas, strange and inexplicable and tantalizingly within reach, reminds us how little we truly understand. Part 15. AI and machine learning-driven public scrutiny of space agency claims. In October 2025, a different kind of controversy erupted, one that parallels the 3I Atlas situation and illuminates the shifting dynamics between institutions and the public. A graduate student at MIT trained a machine learning model to predict asteroid brightness curves based on orbital elements, composition, and rotation parameters. The model ingested decades of observations from NASA's Near-Earth Object Database, learning patterns that correlated object properties with observed brightness over time. The student then applied the model to predict brightness curves for asteroids observed by NASA's NEOWISE mission. an infrared space telescope that surveys near-Earth objects. For most asteroids, the predictions matched observations closely, but for a small subset, roughly 5%, significant discrepancies appeared. The observed brightness was either higher or lower than the model predicted by margins too large to attribute to measurement error or natural variability. Curious, the student investigated further. They requested the raw NEOWISE data for the discrepant asteroids and found that in several cases, the published brightness values had been adjusted during data processing. The adjustments were documented in technical notes but not prominently flagged in the public database. The reasons for adjustment varied: correction for detector saturation, removal of background contamination, recalibration based on updated instrument models. The student published their findings as a preprint, arguing that while the adjustments might be scientifically justified, the lack of transparency created a credibility problem. Users of the public database assumed the published values were direct measurements, not processed and adjusted values, and in cases where the adjustment significantly changed the interpreted brightness, the object's properties, size estimates, composition inferences might be affected. NASA responded quickly. They acknowledged that data processing involves adjustments, and that those adjustments are documented but perhaps not sufficiently accessible to non-expert users. They emphasized that the adjustments improve data quality, and that raw, unadjusted data is also available for users who want it. They committed to making the processing notes more prominent in the database interface. But the controversy didn't end there. Other researchers began applying similar machine learning audits to different data sets: orbital elements for comets, brightness measurements for exoplanets, spectroscopic data for distant galaxies. In each case, a small percentage of discrepancies appeared, most explainable by documented processing choices, some less clear. The pattern revealed something important. Institutional data processing involves choices, judgment calls about how to handle noisy measurements, calibration uncertainties, instrumental artifacts. Those choices are scientifically defensible, but not always obvious to external users. And when machine learning flags discrepancies between processed data and model predictions, it raises questions about whether the processing introduced bias or error. For 3i Atlas, this pattern is directly relevant. Independent observers claimed to see the object during conjunction, but NASA's messaging implied it was unobservable. If an AI audit of coronagraph data detected 3i Atlas, would NASA acknowledge the detection, or would they argue that the AI is flagging artifacts and that proper processing would remove the signal? The asteroid brightness controversy shows that this tension between raw data and processed data, between external analysis and institutional interpretation, is widespread. The democratization of analysis tools, especially AI, means anyone with computational resources can audit public datasets. They can check whether published findings match raw data. They can flag discrepancies. They can ask uncomfortable questions about processing choices. This is healthy for science in the long run because it increases accountability. But it's challenging for institutions accustomed to gatekeeping interpretation. NASA and other space agencies have adapted to their credit. They've increased data release speeds. They've made processing pipelines more transparent. They've engaged with external audits more constructively. But the relationship remains asymmetric. Institutions have expertise, resources, and authority. External auditors have access, tools, and skepticism. Balancing those is an ongoing negotiation. 3i Atlas might accelerate that negotiation. If independent observers using publicly available data make claims that NASA hasn't addressed, and if AI audits support those claims, pressure will mount for more direct engagement. NASA can't simply say, "Trust us, we're the experts," when the public has tools to verify for themselves. They have to show their work, explain their reasoning, and engage with alternative interpretations transparently. The MIT students' asteroid audit established a precedent. Machine learning can be used not just for discovery but for verification and accountability. Algorithms can check whether institutional claims align with available data. They can flag discrepancies that might indicate errors, processing artifacts, or genuine anomalies. And they can do this at scale, auditing thousands or millions of data points in ways human review never could. Imagine applying this to 3i Atlas. An algorithm ingests all publicly available coronagraph images, Mars orbiter frames, ground-based observations, and solar probe environmental data from the conjunction period. It searches for signals consistent with the predicted position and brightness of 3i Atlas. It flags detections, assesses confidence levels, and compares results across instruments. Then it generates a report. Object detected with 70% confidence in coronagraph data from October 28th through October 30th. No detection in Mars orbiter data. Marginal detection in ground-based amateur stacks. That report would be more credible than any single independent observer post because it's systematic, replicable, and transparent. It wouldn't settle whether the detections are real or artifacts, but it would frame the debate more rigorously. And it would force NASA to respond substantively, explaining why their analysis differs from the algorithm's findings if it does. We're not there yet. The AI audit tools are still maturing, access to data is improving but not universal, and the expertise required to apply these tools correctly is still concentrated in specialized groups. But the trajectory is clear. Within a few years, maybe less, AI-driven public scrutiny of space agency claims will be routine. Institutions will have to anticipate and prepare for external audits. Transparency won't be optional, it'll be necessary for maintaining credibility. 3i Atlas is happening at the leading edge of this transition. The independent observers are early adopters, using available tools to question official narratives. The AI community is watching, sensing an opportunity to apply their methods to a high-profile case. And NASA is navigating carefully, balancing transparency with the need to avoid premature conclusions. The outcome will shape future interactions. If NASA engages constructively, acknowledges valid criticisms and integrates external findings into their analysis, trust strengthens. If they dismiss or ignore external audits, trust erodes. And in an era where trust in institutions is fragile, where misinformation spreads rapidly, where the public demands accountability, the choice NASA makes matters beyond just this one object. Because 3i Atlas is a test case, not just for whether an interstellar visitor is natural or artificial, but for whether science in the 21st century can adapt to a world where expertise is distributed, where data is public, where algorithms challenge human interpretation, and where the boundary between professional and amateur, between institution and individual, is increasingly blurred. The universe doesn't care about our organizational charts, it just is. And our job, collectively, is to figure out what it is, using every tool and every perspective we can muster. 3i Atlas is teaching us how to do that, one anomaly at a time. October 29th, 2025 came and went. The date we were told marked a disappearance. The date NASA said 3i Atlas would slip into invisibility. But the independent eyes that kept watching saw something else. They saw light where there should have been darkness. They saw motion where there should have been stillness. They saw an object that refused to follow the script. December will tell us if they were right. December will reveal whether institutions can adapt to a world where the public doesn't wait for permission to see. December will show us whether 3i Atlas was just an exotic comet, or whether it was something that changes everything. Until then, we live in uncertainty. And maybe that's exactly where we need to be. Because certainty closes doors, uncertainty keeps them open. And somewhere out there, in the space between what we know and what we fear to imagine, the truth is waiting. Not hidden, not behind anything, just out there, glowing, moving, breaking every prediction we dared to make. And when we finally see it clearly, when the conjunction ends and the observations confirm or deny what independence claimed, we'll know whether we were looking at a comet or whether we were looking at something looking back at us. Either way, the sky will never look quite the same again.